real gases. Now we are going to go into more detail about real gases. Of course, all gases that we work with in real life are real gases, but there are conditions that we can treat them as we have been with ideal gases, in times when we need to take into account their non-ideality. So we're going to cover all that here. We're going to identify how real gases are different than ideal gases, and under which conditions we can treat real gases as ideal gases. And finally, if we must treat a real gas as a real gas, we'll learn an equation for this. So let's remind ourselves of what an ideal gas is. There are no attraction between molecules, and the molecules are point masses. Or in other words, there is no atomic volume. Before moving on to the next slide, take a moment and think about under what conditions the temperature and pressure of a gas is more likely to act ideally. Let's start with the issue of no interaction. Ideal gases have no interaction with each other. However, real gases do have interactions, and we're going to learn more about the interactions that those occur under in later chapters. So for now, we can't really talk about intermolecular forces for different gases, but we can talk about the attraction within a gas. Attractions are minimized by faster moving particles. The faster the particles, the less interactions. Therefore, in general, small molecules and high temperatures lead to a more ideal gas. Later, you'll learn more about intermolecular forces, and molecules that have low intermolecular forces are also more ideal. Another way of phrasing this, then, is that when molecules are moving slower, attraction becomes apparent. So at high temperatures, or at low temperatures, high masses, and high intermolecular forces, we have to deal with the attraction. It does matter, and it may make a gas real as opposed to ideal. The next issue that comes into play is that in ideal gas, molecules are point masses, meaning that each atom has no volume. So if we want to treat real gases as ideal gases, we need to consider how much of the volume of the molecule matters. Think about a container that does not have very many molecules in it. If there are only a few molecules, the percent of the volume that is taken up by the molecular volume is very, very small. It's like an empty room, or in this case, an empty Times Square. There's not that many people, and so there's very little volume that is taken up by the people. However, if instead there's a much larger amount of molecules, then the volume begins to matter more. So now think of a crowded Times Square on New Year's Eve. The people come in close contact with each other, and suddenly the volume of the people really makes a difference in comparison to the empty volume of the street. So if we want to treat a gas as ideal, we need the volume of the molecules to be negligible. This occurs when there is a very low number of molecules. Or, in other words, it occurs at low pressures. So at low pressures, gases are more ideal, and at high pressures, they are less ideal. The higher the pressure, the more likely that you need to treat it as a non-ideal gas. We need to introduce a measure here that tells us about the molecule's closeness to ideality. Here we have 4 gases at a variety of pressures. You can see how, as you move away from 0 atmospheres, it starts to deviate from ideality, and it moves further and further away. The further from 1 the compression factor is, the less ideal it is. Also notice the zoomed in version of the plot, which is showing you closer to atmospheric conditions, the situation. This is just to help put everything in perspective with the actual values that we tend to deal with in normal life. Now that we have all of the information out of the way, let's apply this to some examples. Take a minute to look at the question. Let's say that we have 2 samples of gas and they are at the same temperature and at identical containers. In one container, though, there are 5 moles of the gas, and in another there's 1 mole of the gas. Which gas is least likely to be able to be treated as ideal? Well, the higher the number of moles, the more pressure that exists. And so the one with 5 moles has a higher pressure and is the least likely to act ideally. Now let's move on to another example. Let's look at this question. If we have a sample of methane, and it is at 50 degrees Celsius and 20 atmospheres, and then we reduce the pressure to 1. Now we're going to assume here that this does not change the temperature. Otherwise, we would have to account for that as well. Is it more or less ideal than in the first sample? Take a second before moving on. Since we'd be decreasing the pressure, this would make the gas more ideal. Now let's take that 50 degrees and 20 atm sample, so the original sample, and reduce this temperature to negative 50 degrees Celsius. What will this do in terms of ideality? Once again, assume that this does not change the pressure. Take a second and think about this before moving on. Since we'd be decreasing the temperature, it would be less ideal. Now, let's talk about what we do if a gas is not an ideal gas. In situations where gases are not acting ideally, we need to be able to handle it. And one of the ways is by using the van der Waals equation. This is an empirically determined formula where the values for A and B come from running the experiment and seeing what fits best. This is only one of the ways in which deviations can be accounted for. There are other equations, but we're not going to go into them in this class. Because A and B are experimentally determined, these are not values that you have to know. You would always be given them because they are giant tables that are based on each individual gas. So let's work through some exercises. For the most part, these are just longer versions of the ideal gas law. Anything that we did for an ideal gas, we can do here. It's just that the algebra gets a lot rougher. On your homework, you may have to do some cubic equation solving. You are welcome to just use the internet calculators for this. On an exam, the most you'd be asked for is to solve for a quadratic equation. So don't spend a bunch of time learning how to do the cubic algebra equations. It's not a big deal. So let's look at this problem. We have all the given information and our van der Waals equation. So this is effectively a very long plug and chug equation. We can fill everything in. Now remember, I give you A and B, so you don't have to memorize those. They're on the slide, or you would look them up in a table. Also, please forgive my lack of units. There's just not enough room on a slide to put them on here. I would suggest on your notes actually including them, but it does not quite work here. So once we get this, we can solve for our answer of 74.3 atm. In review, gases are most ideal at high temperatures and low pressures. Smaller gases with low intermolecular forces are more ideal than larger gases and higher intermolecular forces. If a gas does not act ideally under the given conditions, we can use the van der Waals equation to calculate the conditions.